Hello friends, welcome again and let us discuss some more questions from the subject of machine design under this series, that is the concept through questions, right? We have already discussed some of the questions in earlier video, and let us now let us try to cover a few more topics over here in this particular session. So today I am going to discuss some of the questions from the topics. One is fatigue loading and then the gear design. So those two topics will be covered today in this particular. So let's go ahead and see and try to attempt a few questions over here. So this is the first question for you. Just go ahead, see this question and try to find the answer. It's pretty simple, nothing special in it. Only it checks your basic understanding, right, of this particular topic. So this is from the stress concentration in a machine component of ductile materials is not so harmful as it is in the brittle materials because, right. So first, okay, just go through it and then I will explain it. But first thing that you need to know, in case of these questions, when it is mentioning, making the comparison between the ductile and brittle materials, nowhere is mentioning whether he is talking about the stress concentration for the in static loading or stress concentration in the dynamic loading. See, when we talk about the stress concentration in the static loading, then obviously you know that in ductile materials, whenever you are having, wherever you are going to have the discontinuity because of localization of the stresses, right? Let's say if I take this a sharp notch over here, or let's say this is a sharp discontinuity in the material. This is the shape of the, let us say particular, it could be like a plate or maybe it could be a bar. So here you are having a sharp discontinuity, right? This is a sharp discontinuity, and so when you will apply a load, obviously stress gets concentrated over here, right? I am talking about the static loading. When stress gets concentrated over here, then local yielding will take place. Local yielding, that means because of the localization of the stresses, that means higher value of stresses will be acting over here, and therefore material will yield in this region for the ductile material. So this discontinuity is not going to remain that sharp as it was earlier, and therefore you can say once it will yield, it will become something this way. Same happens over here also. So that means because of the local yielding stress, that means that discontinuity does not remain that sharp, and therefore stress redistribution takes place, and therefore overall value of stress will come down. And that is why we say in case of static loading, we don't apply the stress concentration factor. Because why? Because of this stress redistribution, because of the local yielding of the material. So they are not harmful. That is why we say in case of static load. But when we talk about the dynamic loading, because the nature of failure is same for dynamic and static loading, when the component is, nature of failure is same for the ductile as well as for the brittle material. When the component is subject to dynamic loading, in that case stress concentration plays a big role for both of these materials. Now let's see, stress concentration in the machine component of ductile materials is not so harmful. That means when he's saying this is not so harmful, definitely he's talking about the static loading. Otherwise there is no other option, right? He should have made it more clear, but if he has not made it more clear, then it is understood that he is talking about the static loading only, as it is in the brittle materials. Because why? Because ductile materials local yielding may distribute stress concentration. Distribute means, that means when the stress will get localized, redistribution of stresses will take place, and therefore the maximum value of stress will come down, and therefore that effect of that particular notch or the effect of that particular discontinuity will not be as severe as in case in brittle materials. There is no yielding, as simple as there is no yielding, then obviously the stress concentration effects are going to be significant over there. So the answer is going to be A over here. So let us now see the next question, and it is about the SN curve. So SN curve represents what it represents basically, or rather how basically SN curve is, in which particular diagram it is represented. So he has given the y-axis and x-axis, and you also know very pretty well that when we draw the S over here stands for what? SN diagram, we know, even though we represent the stress amplitude in a very conventional way with the stress amplitude with sigma A and mean value of the stress this way, but while drawing in the SN diagram, basically that SN diagram stands for, basically S stands for the stress amplitude only. Sometimes we can say this SF also. These are the different terminologies which are used over here to represent. That means on Y axis you are having this fatigue, or you can say stress amplitude. I can say stress amplitude. So should I say this way, SF, S, but and over here N. N is the number of stress reversals, right? So normally as you know, we represent it in log graph. So I can say this is log of what? S. So this is the stress amplitude. Indirectly we can also say, when we draw that diagram, if you recall, this is something this diagram looks like. So this values of these particular stresses, stress amplitudes, any stress amplitude corresponding over here, corresponding to the number of stress cycles, what we call it as a fatigue strength also. What does it mean? It means that means to get a life of this much number of stress cycles, what is the amplitude of the stress that can be carried corresponding to those number of stress cycles. Let me repeat what I said. I said, if you want a life of a certain number of stress cycles, then to get that life, what is the magnitude of what is the amplitude of the stress that can be applied on that component? You said this is the amplitude of the stress that can be applied on that particular component, right? This is the amplitude. So this amplitude of the stress to get a particular number of stress cycles, we call it as a fatigue strength also, right? So you can say, even though it is this stress amplitude only, but we can also call it as a fatigue strength, but you have to interpret in the way that means why fatigue strength? Fatigue strength, how will you say that is the fatigue strength? Fatigue strength mean, fatigue is what? The failure due to crack. That means, what is the amplitude of the stress that is going to produce the crack in the material in these number of stress cycles? That is the meaning of this. So that becomes the fatigue strength of the material, as simple as that. So fatigue strength of the material is simply the stress amplitude that the material can carry for a certain number of stress cycles, right? Or this is for the finite number of stress cycles. The same thing we can call for the endurance limit also. The endurance limit is over here. So this is, what is this? This is the stress amplitude. Again, this is what? Endurance limit is what? Keep it in mind, this is in log only, but I am writing it for the sake of simplicity. That is the stress amplitude. Let's say, what is that? I will represent this way. Let's say if I write it this way, this is my notation, okay? Anyway, so you can denote it by anyway. So in by any term and all that. So this is the amplitude. Now see, this is the fatigue strength, but this is the fatigue strength for what? Endurance limit is the fatigue strength for what? For the unlimited number of stress cycles. That means this is the amplitude of the stress that a component can carry for unlimited number of stress cycles without any crack generation. This is how you have to see. But anyway, so that's you know already. So that means SN diagram basically represent the fatigue strength on y-axis. That means stress amplitude on y-axis, right? Either you represent this way, but standard terminology is because we say when the Horler represented this diagram first time, so he denoted that stress amplitude with S, or sometimes it can be represented with SF. So whatever you write, stress amplitude and number of stress cycles and number of fully reversed stress cycles. So you know that means this SN diagram is for the completely reversed stresses. That is why the fully reversed stress cycles. Okay, so that means as simple as that. This is the C is going to be the answer. Okay. So let's now move ahead. So this is the answer for you. Let's see the next question. Here's the next question. Notch sensitivity. What does the notch sensitivity says? So all of you have studied about the notch sensitivity also, right? So let us see what is the meaning of notch sensitivity. That means how sensitive the material is for the effect of notches, right? So you already know, let us say, in case of, let us say, I want to find out the stress concentration factor for actual materials. So how do you write? You write it stress Kt minus 1, right? That is how you write the stress concentration factor, right? So if material is, so this Q is the notch sensitivity. So it could be for static loading also, for the fatigue loading. In that case, this becomes the fatigue stress concentration factor will become equal to 1 divided by notch sensitivity in fatigue Kt minus 1. This is how it is. So this is for static loading, this is for the fatigue loading, this is for the, so when you want to find out the stress concentration in the material, actual materials, then we basically, encounter a term called as notch sensitivity. That means how sensitive that a material is for the effect of the notches, whether it is in static loading or whether it is in what? Dynamic loading. See, this range, first is that normally it varies from 0 to 1. This is the kind of factual information we need to have. But what is the meaning of that? When we say notch sensitivity is 0, it means material is not sensitive to notches. In static loading, if I say which material is not sensitive to notches, so I have already discussed with you. Ductile materials are not sensitive to notches. Why? Because stress redistribution takes place. Stress redistribution takes place. So that means the overall value of stress will come down in that particular discontinuity. So it means ductile materials are not sensitive for notches in static loading. That is why what we use? Q becomes 0. Q becomes 0, this term becomes 0, K become equal to 1. That's all. So that means we don't make use of the stress concentration factor for the ductile material in case of, for the ductile materials in case of static loading. As simple as that. And what about the brittle materials? Because they don't yield locally and therefore stress concentration is going to play a role. So definitely they are going to have some value of the notch sensitivity. So on one end you are having a ductile material where you can have 0, on the other end you can have brittle material. Depending upon the type of material, brittle material, you can have any 0.2, 0.3, 0.4, 0.5, or it can extend up to the, if the material is highly sensitive, then it can equate to, that brittle material is in static loading is highly sensitive, then Q can even become equal to 1. So this is a case of static loading. So same formula, similar kind of formula you have for the fatigue loading also. In fatigue loading, the material behavior is different, whether it is a ductile or brittle. So over here we were saying for ductile it is 0, brittle you have to use a certain value of Q. But over here you will say notch sensitivity, this Q, notch sensitivity I have to, or the notch sensitivity index I have to use for the ductile as well as the brittle materials, because both behave in the similar manner when they are subjected to the what? Fatigue loading or fluctuating loading. Then in that case, how do we decide that how much is the value of Q? In case of brittle, see, the value of Q in case of fatigue loading is decided by the grain structure. How the, basically what type of, how are the grains or what type of grains are there in that particular material, irrespective of whether it is a ductile or brittle. So that means if the grains are fine, then we say they are highly sensitive to notches. If the grains are very coarse structure in the material, then we'll say they are less sensitive to the notches. So we have one example, I think you may have studied also, that is a, for example, you are having a cast iron, right? Particularly the grey cast iron. Grey cast iron is having a structure in which it's a soft and hard structure, where you are having a graphite flakes and then hard structure. So graphite flakes is like a very soft material, and then the hard structure like cemented and all that is combined over there. Like you may have seen the machine tool beds, like where you need to absorb the certain amount of energy. So there you can make use of these grey cast iron machine tool beds. So because of the graphite flakes present. So that means it's a kind of a highly coarse structure. That means you can simply imagine that the kind of discontinuity that exists in the material. So this kind of different kind of structure like soft and hard, they act as a highly discontinuous structures, and therefore we say that discontinuities, lot of discontinuities are already present in the material, and therefore it is high, the stress concentration is already there present in that material. High, that means level of stress concentration will already be too high in this particular material because it's a coarse grain structure. Now if we introduce one more notch or any small discontinuity in that material, so it is going to have a not much influence in that particular material in reducing the endurance limit, in the sense that since discontinuities were already present over there and stress concentration was already large, even if we add one more discontinuity, it is not going to influence that stress concentration to that bigger amount, and therefore it will not be sensitive to notches. So in that case we can say that for this material the notch sensitivity is almost 0. It is not going to react to the notches because already the material structure was discontinuous, and therefore stress concentration was already large, and therefore even if we add one more notch, it is not going to influence that particular, it is not going to increase the stress concentration by a large amount, and therefore it is not going to reduce the endurance limit of that material by significant amount. So in that case we can say that the material is not sensitive to notches. So in that case QF, fatigue stress concentration, over here it was not a fatigue stress, notch sensitivity in fatigue, and here this is notch sensitivity index when the material is subjected to static loading. So when it is subjected to fatigue loading, then in this the example that I quoted you, so let's say it becomes what? It is not sensitive to become equal to almost near to 1. Now think of the situation where you are having a very fine grain structure, right, in the material, irrespective again whether it is a ductile or brittle, right. We don't talk in terms of brittle and ductile material over here. When we talk about the notch sensitivity, we talk in terms of the grains, fine grains and coarse grains. Coarse grain, highly coarse grain structure, I have already explained you, where you are having notch sensitivity index equal to 0. But if the structure is very fine, then obviously the stress concentration initially will not be that large, and therefore it will have a higher value of, for example, if we say that if the grain structure is fine, then let us say for fine grain structure in the material, you are not going to have that much of stress concentration, and it may have a particular value of the endurance limit, let's say this much. Now if we introduce a discontinuity in this material or notch in this material, then its endurance limit is going to reduce significantly, because when we will introduce the discontinuity, then stress concentration will be significant in the material, and therefore this drop in endurance limit will be significant over here. So now endurance limit will be this. That means in this case, if the material structure is very fine, fine grain structure, very fine grain structure, in that case we will say material will be highly sensitive to notches in case of dynamic loading, as I explained you. Why? Very sensitive to notches mean what? It is going to significantly reduce its endurance limit, because fatigue stress concentration will be more. So in that case you can say that is this notch sensitivity factor in fatigue is going to be equal to what? 1. That is highly sensitive to the notches over here. When it equal to 1, so it becomes equal to KT, that means minus 1 minus 1 cancels out and left out. That means fatigue stress concentration factor will become equal to the theoretical stress concentration factor. That means the material fine grain structure will be highly sensitive to the notches when it is subjected to this dynamic loading, whether the material is ductile or whether the material is brittle. ये आपने ध्यान रखना है. That is how the interpretation is done. So that is why, so one is that how that particular notch sensitivity varies. So you will say the notch sensitivity is going to vary between 0 to 1. So for whether it is a static loading case or whether it is a dynamic loading case, for both cases you could have. The only difference with here, notch sensitivity index we define based upon the ductile and brittle. Over here we define based upon the grain structure, whether it is a fine grain or coarse grain structure, right? Okay, so let's so this is going to be the answer as D. Let's move on to the next question. According to the Gerber method, variable stress is given by. Now for this you need to know simply this, I will draw it over here. So I will draw it here only, right? So this is how, when a component is subjected to fluctuating stresses, that means you are having mean as well as the stress amplitude. So we plot on one axis we plot amplitude of the stress, and on other axis we plot mean value of the stress. This is how it is. And then we are having, say, let's on one end we are having like sigma yt when it is completely static stress, that is no stress amplitude, static stress. Then criteria of failure is this, that you know. And when it is mean is 0, when there is no mean, then stress amplitude, then this becomes a case of completely reversing stress. So in this case mean is 0 and you have only stress amplitude. So when mean is 0, so how is the criteria of failure? You are having the criteria of failure, this SE, endurance limit. So in case of completely reversing stress, when mean is 0, endurance limit criteria is SC, that you know already. So if that is the situation in case of, so now how the component is going to fail, so we will take different, we plot the diagram and all that, then we join these different values. So for the what is that? He's giving for Gerber, okay. So we are having, this is, you already know, this is for Soderberg line. Then if you join with this is Goodman line. And let us say if you have that curve that you join, so this is becomes the Gerber curve, right? So Gerber method, right? Now, so how do we write that? So now, how do we write that particular curve? Basically, Gerber has given the equation for this curve, right? And on the similar lines, like Goodman has given the drawn this line, so obviously you can use the equation of line. Same way, Soderberg also you can make use of the equation of line. So over here, as per Gerber, you can make use of that similar lines पे उसने जो equation दी है for this parabolic curve, that is a sigma A divided by SE. I will make it a little smaller, okay. Okay, so this is sigma A by SE plus what is that, sigma mean divided by what, because this Gerber is joining over here sigma ultimate, and this is square equal to 1, right? This becomes a this is given by this particular Gerber for this curve. So this curve is drawn in such a way that it passes through the maximum points which are scattered over here. So I hope you may be knowing that part. So this is the curve that he has given you, right? Now this is when we are talking about this curve, but when we apply the factor of safety on this, that means factor of safety over here on the endurance limit and over here on the ultimate, because these are two extreme points, right? So when we apply the factor of safety on these 2 points, then obviously what we have to do is the allowable endurance strength will become SC by factor of safety somewhere here. Same way, ultimate will become factor of safety sigma ultimate divided by factor of safety. That point will be somewhere here, right, by applying this. So if we apply the same factor of safety, we are going to have this way. So that means sigma A divided by what? SC by factor of safety. You applied on this particular, same way on ultimate you have to apply. So that means sigma mean divided by what? Sigma ultimate divided by factor of safety square equal to 1. That is how it is going to be, right? So you apply the same factor of safety over here on endurance limit, same factor of safety on ultimate over here. So you can write it this way. So what I will do, I will rearrange it. I will take the factor of safety above, and then I will write it. So it becomes what? So sigma A into factor of safety, he is writing factor of safety by Fs divided by endurance limit plus, so sigma mean into factor of safety divided by sigma ultimate, this is 1 square equal to 1. That's all. So what he is asking you to find out? He is asking you to find out at first this variable value of the stress. Variable stress means amplitude of the stress. So sigma A you want to find out, right? So take it to that other side and then divide by what? Multiply by SC and divide by factor of safety. So can I write it directly? Sigma A equal to, if you rearrange it, if you take it to the other side, 1 minus this value. Now when you SC obviously going to be outside and factor of safety से आप divide करोगे तो 1 by factor of safety and this total term divided by factor of safety. Factor of safety will cancel out, so it will come out to be 1 by factor of safety minus, since it is factor of safety square, so it will turn out to be sigma mean divided by what? So sigma ultimate square into factor of safety. That's all. So you can just see the options, whatever option that you are having over here. So you are having, I think this is the third or fourth one? This one, sigma E. Over here, sigma E is denoting for the endurance limit, 1 by factor of safety minus 1 by sigma ultimate Fs. So C becomes the correct option. So can I write this is the C is going to be the correct option. Say, see, on the similar lines, he can ask you for writing or finding out any particular value. You must be in position to use the equation of line for Goodman relationship and equation of line for the this Soderberg equation. So from there also question could be reframed or rearranged on the similar lines. Okay, so pretty simple. Simply just remember this, and then you will be able to find out the correct answer. Okay, so let us now see the next question. Goodman's straight line relation suggests that variable stress component in the presence of a positive mean stress. थोड़ा wording जो है इसकी ambiguous है, but what it means is simply, which you already knowing if you know the diagram, pretty simple to understand, but he has just made the wording little bit confusing. This you already know, this is the mean stress, right? And this is the, amplitude of stress, this is the mean value of the stress. And if you talk about the Goodman, this is ultimate, and this is what? This is endurance limit, right? This is how it is. Goodman's straight line relationship suggests that the variable stress component, that means this sigma amplitude, in presence of a positive mean stress. So what does this mean? This line states basically that what happens to the amplitude of the stress when the mean stress increases in the presence of a positive mean stress. In the presence of a positive mean stress means as the mean stress increases. Otherwise, you cannot answer it properly. So he has not framed this question very properly in terms of like making the meaning clear. But what I understand from this particular whole of this sentence is that how basically amplitude of the stress varies as we go on increasing the mean value of the stress. So that you can understand, as we will increase the mean value of the stress, the amplitude of the stress that component can carry without the fatigue failure will decrease. So जैसे जैसे mean component बढ़ाते जाओ, amplitude of stress क्या होता जाएगा? So as you go on increasing the mean value of the stress, as you go on increasing the mean value of the stress, amplitude of the stress is decreasing. As simple as that. So this is how it is going to be. This is going to the A is going to the answer. Okay. So pretty simple. Only thing is that he has not worded it very properly. Let's go to the next. The design calculations for members subject to fluctuating loads with the same factor of safety yield the most conservative estimates when? The design calculations for members subject to fluctuating load with the same factor of safety yield the most conservative estimates when? कौन सा क्राइटेरिया यूज करते हो? दैट मीन्स लेट्स से ये क्राइटेरिया था आपके पास, दिस वाज द क्राइटेरिया दैट आई हैव डिस्कस विद यू. Sigma mean, right? Now let us say if I take any particular value of the mean. अब देखो ध्यान रहे कि all of these investigators have drawn these mean lines or curves passing through those scattered points, and the way they chose the criteria, they decide whether based upon that criteria, whatever criteria they have chosen or whatever the lines or those curves they have given, based upon that we will decide whether which one is conservative, which one is not that conservative. As simple as that. Or which one is safer and which one is more accurate. That way also you can say. Let us say if I take any particular value of mean. Let's say मैंने कहा कि एक component है जिसके ऊपर mean value of stress ये लग रही है. Right. Then against the mean value of the stress, the amplitude of the stress that the component can carry as per the Soderberg is this much. Soderberg ने कहा कि ये इससे ज्यादा जो है स्ट्रेस एम्पलीट्यूड कैरी नहीं कर सकता अगर आप मीन वैल्यू ऑफ स्ट्रेस ई अप्लाई कर रहे हो. गुडमैन ने क्या कहा? ये इससे ज्यादा कैरी कर. गुडमैन says that for the same value of the mean stress, the amplitude of the stress that the same component can carry will be this, which is higher than this. And when we go to Gerber, then Gerber says that for the against the same mean value of the stress, the amplitude of the stress that this component can carry, same component can carry is this much. Now which one is correct, which one is not, right? So एक बोलता है कि इतना ही कैरी कर सकता है, दूसरा बोलता है इतना कैरी कर सकता है, थर्ड बोलता है इतना कैरी कर सकता है. Now keep it in mind, most of the scattered points they lie to the right side of this particular Soderberg curve. And when you have gone through these theories, you must have studied that basically the Gerber curve, Gerber had drawn this curve, Gerber had drawn this curve so that it passes through the maximum those points, that is closest to those maximum points. मतलब अगर मेरे failure points ऐसे हैं तो you can just simply think of Gerber is basically the more accurate in predicting the failure of the components subject to this combination of loading. या आप बोल सकते हो most of the scattered points के आसपास से ये Gerber curve जो है that is going through. So if that be the case, so इसका मतलब ये है कि जो Soderberg है यहां पर, Soderberg is what? So actual जो component है जो फेल हो रहा है वो तो बहुत इस सेम मीन वैल्यू ऑफ स्ट्रेस के कंपैरिजन में बहुत ज्यादा स्ट्रेस एम्पलीट्यूड पे फेल हो रहा है, whereas as per Soderberg it is failing over here. So it means Soderberg is playing safe. Soderberg बोलता है कि इतना ही स्ट्रेस एम्पलीट्यूड कैरी कर सकता है, जबकि एक्चुअली हम बोलते हैं Gerber is more accurate because it is passing through this. So actually जो component है वो इतना, let us say even if we take for safety side, let us say this one, let us say this point was not over here, this point was over here, and this curve passed through this. So even if we take this point over here, then compared to Soderberg, this value of the stress amplitude that can be carried is significantly higher by this margin. So it means the component, let's say if this is the component, when subjected to fluctuating stresses, actual amplitude of the stress that it can carry was higher, but Soderberg ने बोला no, it can carry only this much. तो आप क्या कर रहे हो? You are playing safe. अपने आप को क्या कर रहे हो? Conservative. तो आप what you are doing is you are basically, when this is the case, then indirectly what you can say, the ability of this component to carry the stress amplitude was higher, but what you predicted? You predicted that ability of this material to carry the stress amplitude is less. तो जहां मैं इस component को larger value of stress पे subject कर सकता था, when it had the ability to carry a larger stress amplitude, पर आपने एक्चुअल में इसको सब्जेक्ट में डिजाइन किया कंपोनेंट बेस्ड अपॉन Soderberg, तो साइज ऑफ द फॉर सेम साइज ऑफ द कंपोनेंट यू आर सब्जेक्टिंग टू लेसर वैल्यू ऑफ स्ट्रेस और लेसर वैल्यू ऑफ स्ट्रेस एम्पलीट्यूड, तो आप क्या हुए? कंजर्वेटिव हुए. इट्स समथिंग लाइक हैविंग ए लाइक यू आर हैविंग those static loading में you are having this we are saying shear stress theory and for ductile materials and the distortion energy theory. What do we say over there? Same thing we say in distortion energy theory. What we say is that it is more accurate. More accurate means it is close to the actual failure points, whereas shear stress theory हम बोलते हैं क्या, that is not that accurate, it is away from this. तो इसका मतलब है in that case it is more conservative compared to the distortion energy theory, as simple as that. So you are playing more safe, you are playing more safe, that means you are more conservative in approach. That means more conservative in approach means that dimension of the component that you are taking to carry a smaller value of stress, larger indirectly you can say larger this dimension of the component you are taking in order to carry the same magnitude of the stress when we compare these theories, right? So that way you can say, so out of all these theories you can say the most conservative is going to be what? Soderberg. Least conservative, the question is framed, which one is the least conservative? You will say Gerber is the least conservative out of all these because it is close to this. So इसमें इसने कुछ नहीं कहा है कि fluctuating loads with the same factor of safety. Obviously when we will design factor of safety तो हम लोगे ही, तो factor of safety इसके लिए भी same होगा, इसके लिए भी same होगा. When we will design based upon that, yield the most conservative estimate. कौन इनमें से factor of safety लगाने के बाद भी कौन इनमें से जो है that is going to give you the most conservative estimate. तो factor of safety तो same ही लगा रहे हो आप, whether Gerber के ऊपर भी same लगा रहे हो, let us say, और इसके ऊपर भी same लगा रहे हो, Soderberg के ऊपर भी same लगा रहे हो, तो then the analysis is going to be on the similar line as I discussed with you. So most conservative is Soderberg. So this is going to be the answer is going to be the what? B, right? Okay, so let us now see a few questions from this gear design section. So here is the first question for you. When both pinion and gear are made of the same material, then from the design point of view, Which one is the determining factor? Right. So see, as you know, when you start the gear design, we come across the beam strength of that particular gear tooth, right? How do we write the beam strength of that particular gear tooth? You know it very well. So if I want to write the beam strength of the gear that tooth, so how you can write? So beam strength, you can write it very clearly, is how we denote it with SB. So beam strength is what? The maximum tangential tooth load that your gear can carry, gear tooth can carry, tangential tooth load that your gear tooth can carry without any bending failure. That is the beam strength of that particular gear tooth. So how do we write? This is a allowable value of bending stress for that particular gear material, and you are having B, M and pi y. This is how the beam strength can be found out. So over here, if you see pi y is the Lewis form factor, where sigma b allowable is the allowable bending stress for the material, b is the width of the gear tooth, and m is the module. Now, while deciding which one is based upon which, whether we have to design that gear tooth based upon that or that gear based upon the pinion or based upon the gear, what are the deciding factors? See, whether the material is same or different, that particular B, width of the gear tooth is going to remain same, right? So if I say that this is the gear tooth, so obviously for any two mating gears, this width has to remain same, and also module in any case has to be same. So width as well as the module of the gear tooth. If you want the proper mating, then module has to be same for any two mating gears. Pi is constant. So deciding factor now about the beam strength is the Lewis form factor, that is the small y over here. Pi into small y, together they are also called as capital Y. So that is also known as Lewis form factor. So whether you call it as a small y or capital Y, it is a Lewis form factor. Only difference being that capital Y is the small time the small y. And sigma b allowable is the material property, the maximum value of the stress, bending stress that material, material of those gear tooth can, those particular gear teeth can carry, right? So it means, let us say, when these pinion and gear are made up of same material. So what does this mean? That means the maximum value of the stress, bending stress, both these materials can carry will be same. So it means whether when the material is same for both the gear and pinion, that means the allowable value of bending stress is also going to be remain same for both of them. So beam strength of either pinion or gear, which one is going to have a larger or smaller value of beam strength, will be decided by the Lewis form factor. So if you know about the Lewis form factor, then I think you will come to know about the beam strength of that particular gear tooth, whether it is a pinion or gear. And at the same time, he can also frames the questions from here. As you know, I can write the Lewis form factor, Lewis form factor small y. How you can write? So these are the some of the equations that you need to remember, that how we can calculate the y, because he can straightforward ask you that particular relations also, right? So for example, if I take so this is 0.95 divided by z. So see, Lewis factor is given by this, where z is the number of teeth on the gear or in the particular pinion. So that is for the when you are having a pressure angle of 5.5 full depth. So when you are having 15.5 degree full depth system, gear system, then Lewis form factor could be found from this equation. Same way, when you are having a gear 2 system having 20 degree full depth pressure angle, then you can make use of this equation, 20 degree full depth. And when you have the 20 degree stub teeth system, then you can make use of this particular equation. So you have to remember it sequentially this way only, and he can ask you to any one of these. He can give you the, okay, for 20 degree full depth involute system, the Lewis form factor is given by what? So he may give you all these values or some other additional value. You must be able to identify. That way also you can frame the questions. Now my point was, so when you are having these two, that means when gear and pinion are made up of the same material, then if you see now Y, now when in which case Y is going to be smaller, right? Because for either pinion or gear, whichever is having the smaller value of Y, the beam strength of that will be less. That means the load that particular pinion or gear is going to carry will be less. So what we have to do is we have to design that gear set based upon that weaker, because if we will make that particular, because same amount of tangential tooth load will be acting on those connecting gears when you want to transmit the power. So if you want to transmit the power, then tangential tooth load which is acting over here, that is same for this gear as for this pinion as well as gear. So how much this tangential tooth load I can apply will be decided by the weaker out of these two. So if let us say this pinion can carry only 10 Newton of the tangential tooth load, whereas gear can carry 15 Newton of gear tooth load. So I cannot apply the 15 Newton of the tangential tooth load, because in that case this pinion is going to fail. But if I apply the 10 Newton of the load, then obviously pinion can also carry and the gear can also carry. So out of these two, I want to find out which one is the weaker, or which one of these two have the lower capacity to carry the load, because based upon that I am going to design. Only then this whole system is going to be safe. So now it means out of these two, that means gear or pinion, whichever is going to have a smaller value of Y, that is going to have a smaller value of beam strength. Or basically what is the beam strength? This is basically the beam strength is basically this is the maximum value of the tangential tooth load that the gear or pinion can carry. It is the same thing. So whichever is going to have the smaller value, I will say I am going to design based upon that. Now see the equation. Any one of these equations can be taken, and if you can take any one of these equations, let us say I am saying 1.24.684 divided by Z. Let's say this is the Y, right? Now you know gear is larger, pinion is smaller. So let us say if I take the pinion is having smaller number of teeth compared to gear. So if this value is smaller, this term is going to be larger. If this term is going to be larger, here you are having the minus sign, the total value is going to be smaller, because this is in minus. So if this value is larger, then obviously when you minus find out this value, this total value is going to be smaller. So it means Y, Lewis form factor, is going to be smaller always for the pinion. So if Y is smaller always for the pinion, and also at the same time gears are made up of the same material for which this value is same for pinion and gear, then obviously beam strength will be smaller for the pinion. Beam strength means the tangential tooth load that the pinion can carry will always be smaller than the gear, and therefore we have to make it safe. That is, we have to make pinion safe first side. So if pinion can be made safe, then obviously gear is always safe, because gear has larger capacity to carry the load, and therefore design will be based upon pinion only, right? So that means here the answer that you are going to have will be the pinion is the determining factor. Am I clear? The question could also be framed that if the gear and pinions are made up of different materials, in that case, which one is the deciding factor? So you know whether they are made of the same material or different material, width and the module is always going to be same. Pi is a constant. So that means when gear materials are different, in that case this allowable value of bending stress is going to be different, because material is different, it's a material property. So that means this is going to be different for pinion as well as gear. Y is different for pinion as well as gear. So then the deciding factor is the combination of sigma y, B allowable and the Y. So what we will do in that case, we will check this value B allowable into Y for gear as well as for the pinion. Whichever is going to have the smaller value, that will be having the lesser beam strength, and therefore we will design based upon that. It could be gear, it could be pinion as well. So in that case, you cannot decide solely based upon the Lewis form factor. You will decide based upon what? This combination of Y and this. So that way also question could be framed. So I hope you got. So 2-3 questions could be framed from on the similar lines, right? One is this, another one is already asked, and third one could be like if that combination is different. Okay, so over here you are going to have the answer. For accurately cut gears operating at velocities up to this, the velocity factor is equal to. Now, where do we use the velocity factor? Right, you already know that this is the tangential tooth load, right? Normally we calculate it at the pitch point, right? So this is the tangential tooth load. The same tooth load, if it is maximum tangential tooth load that you can apply over here between the two mating gears to avoid the bending failure, that time we said this is the beam strength. But let us say this is the tangential tooth load. And from where did you calculate that? You calculated this from power. Power is equal to 2 pi nt divided by 60. कितना टूथ लोड यहां पर लग रहा है, टेंजेंशियल टूथ लोड लग रहा है यहां पर, that will come from power that you want to transmit into the two mating gears. So n is the speed, and what is T? Torque. And how I can write it? What is the load that is acting over here? And if this is a radius, so I can say this is the pitch circle radius, R. So this becomes the tangential tooth load into R. Right? So this is how basically, that is power. From the power you will come to know, power will be given to you, and obviously how much speed at which that particular pinion or the gear is rotating. If you put it over here, if you know the radius of that pinion or gear, you will come to know how much tooth load will be acting over here, how much is acting over here. That you will come to know. Now, this is the tangential tooth load from the power, but you know, and based upon this value, the Lewis basically designed the gear for the bending stresses. But you know, when the gears are running at at higher speed, and actually they are running at higher speed, then dynamic loads are also present, right? So since dynamic loads are present over there, right? So because of those dynamic loads, right, additional load will be acting on the gear tooth. That means this was simply based upon the power calculation. Based upon power, this much, if this much power you want to transmit, even the speed is very less, let us say, whatever maybe this speed is very less. So even then PT will be acting. So this tangential tooth load that you have calculated, basically you have calculated based upon the power. But this is always acting when you want to transmit a certain amount of power. But in addition to it, additional load, some additional load will also be acting because of the dynamic factors present in that particular system as you are running at a particular higher speed. So in that case, how to calculate that actual force which is acting over here? We call that force, you may be knowing, we call that force as P effective. And that effective force will be calculated by two methods. One is by making use of the Buckingham equation, and the second one is by making use of the velocity factor. Ultimate purpose क्या होना चाहिए? वो जो effective tooth load है, that will always be greater than this tangential tooth load. ये तो लग ही रहा है, इसके अलावा क्या लग रहा है? तो दो तरीके हैं. There are two ways to calculate. One is either you calculate it separately. तो मैं बोलूँगा ये total tooth load, total और effective tooth load कितना लग रहा है? This much is always acting, plus in addition to it there will be some additional load acting. Incremental additional load which is acting, that is given by the Buckingham equation. So this is the additional tooth load. I can call it as a PD, as a additional tooth load. Am I clear? So ये तो आपको पता है कि ये लगेगा, या तो एक तरीका ये है, दूसरा तरीका क्या है कि इफ यू डिवाइड बाई ए फैक्टर, इफ यू डिवाइड बाई ए फैक्टर, अगर ये तो था ही, इफ आई डिवाइड दिस load by a factor so that total value increases. So what I do, if I divide, or you can say, or there could be another method where we divide the load with a factor, some factor, let us say, whose value is less than 1, then the total value will become more than this. When you add some load over here, there are alternate ways. यहां पर आपने add किया इसके ऊपर तो टोटल वैल्यू बढ़ गई, यहां पर क्या किया, यू डिवाइडेड बाय अ फैक्टर व्हिच इज लेस देन 1, टोटल वैल्यू क्या होगी, बढ़ गई. दैट इज व्हाट आई वांट टू नो. आई वांट टू नो द एक्चुअल लोड, इफेक्टिव लोड व्हिच इज एक्टिंग, दैट विल बी मोर देन दिस. दिस आर टू वेज. सो ये बकिंघम इक्वेशन से निकलता है. ये जो है वो बार्थ ने केवी की वैल्यू जो है ओवर हियर इज आस्किंग द वेलोसिटी फैक्टर. वी कॉल दिस फैक्टर एज ए वेलोसिटी factor. So how can we calculate that velocity factor? So that velocity factor is given by the Barth, was given by the Barth for different speeds of the gears at which they are running and the accuracy level. So where kV is the velocity factor, and so I can write it this way, where kV is the velocity factor or dynamic factor. Am I correct? How can we? It is given by Barth. So as per Barth, जो उसकी values हैं, name of the investigators, so I can find out the value of kV over here. I think I have that much space over here. kV I can write, there are 3 divided by 3 plus V, 6 divided by 6 plus V, and okay, I will write it over here so that I have space. Okay, so where kV is dynamic factor and kV can be given as ये 3 वैल्यूज हैं. सो ये वैल्यूज भी वो आपसे पूछ सकता है. ही कैन आस्क इवन दीज वैल्यूज फ्रॉम यू, दैट नाउ दिस वैल्यू इज फॉर द व्हेन यू आर हैविंग ए काइंड ऑफ कमर्शियल कट गियर्स के लिए हम बोल देते हैं kV जो है दैट शुड बी, दैट मींस दे आर नॉट वेरी हाईली एक्यूरेट, बट हम उसको सिंपली बोल देते हैं, टर्म यूज किया जाता है व्हिच आई एम फॉरगेटिंग, दैट इज ऑर्डिनरी और कमर्शियली कट गियर्स, राइट. ऑर्डिनरी और कमर्शियली कट गियर्स, कट गियर्स with pitch line velocity less than 10 मीटर पर सेकेंड. तो अगर आपके गियर्स जो हैं दैट इज कमर्शियली कट, दैट मींस नॉट वेरी हाई डिग्री ऑफ एक्यूरेसी, in that case they can be done at a velocity, pitch line velocity which is less than 10 meter per second, then we can make use of the velocity factor as 3 by 3 plus V. But if they are accurately and hobbed, hobbing is a process as you may be, accurately manufactured and hobbed, so उस केस में with pitch line velocity, that means we can use the higher velocity 20 meter per second. Okay, then we will use this. And if they are precision cut, like you have done lapping, you have done honing, kind of not honing, lapping and grinding, then precision cut, then the accuracy is too high, then I can even go for the higher speeds also. So in that case I can say that is precision cut gears, precision cut gears with velocity, pitch line velocity greater than 20 meter per second. So if these are the situations, then you can make use of these, any of these relations to find out the velocity factor and input over here, and you can find out the actual tooth load. So ये ध्यान रखो, इसको याद रखना, and these values also you need to remember, and just use these values and you can find out. So over here also he can give you to how we can find out the effective tooth load, either this way or this way. He can also ask you to calculate that way also. So 2-3 questions could be framed from here also. So over here straightforward now we can go, and that means for accurately cut gears operating accurately and hobbed gears, you can say velocity up to 20 meter per second, this one, the velocity factor is 6 divided by 6 plus v, and keep it in mind this v over here is going to be meter per second when you find out this particular factor. Okay, so this is how you have to find out the answer. Let's go to the next one. Just have a look. Surface endurance limit of the gear material is dependent on surface endurance. See, as you know, as the gears are moving and they are rubbing against each other also, and therefore not only rubbing but also at the same time they are subjected to repeated loading. Repeated, like two gears came together and then they applied the load, and then after one complete revolution again they will come in contact. So repeated loading, cyclic loading is also acting. So, and over here when they are coming in contact, they are compressing each other, right? So what may happen that because of the cyclic loading, surface fatigue failure may take place. That means surface fatigue failure means failure of the material on the surface. Kind of surface से ही आपका material जो है वो crack generation के through बाहर निकल के आ गया, right? So उसको हम बोलते हैं, तो there you are going to have the surface endurance strength is going to play an important role. So that's what he is saying, surface endurance limit of the gear material. See, endurance limit in general for the material, but when we are talking about specifically talking about the surface, then surface में crack ना आए और surface में ही आपका material remove ना हो जाए in the form of like small chips or small this. So for that we use the surface endurance limit of the gear material is dependent on what? You can just see अब देखो, अगर आप वो चीज इंप्रूव करना चाहते हैं, वियर डज नॉट टेक प्लेस सो इजीली. अगर वियर जब आप उसको जो क्या कर रहे हो, रोल कर रहे हो और सरफेस के ऊपर जो क्या हो रहा है, वियर डज नॉट टेक प्लेस सो इजीली. व्हाट इज द थिंग दैट यू नीड टू मेंटेन? यू नीड टू मेंटेन द सरफेस प्रॉपर्टी, पर्टिकुलर द हार्डनेस. अगर आप हार्डनेस इंप्रूव कर देते हो, द वियर आउट विल नॉट टेक प्लेस, राइट? और जो रिपीटेड लोडिंग हो रही है आपका, उसके कारण जो है वो सरफेस से मटेरियल इट विल नॉट पील ऑफ सो इजीली. सो दैट इज व्हाई if you see the surface endurance limit of gear material is dependent on its what? Not all these other things, but on the Brinell hardness number. So as you know, this is one of the number which is used to represent the hardness of the material. So that is why if you see the gears are basically surface hardened, so that wear does not take place so easily, or surface fatigue failure does not take place so easily. So C is going to the correct answer. Let's move on to the next question. Gear teeth are made harder to avoid. क्यों हार्डनेस बढ़ाते हैं हम? राइट, सो ऑब्वियसली यू विल से टू अवॉइड द वियर फेलियर, बट यहां पर इन्होंने एक और टर्म यूज कर दिया, पिटिंग फेलियर. पिटिंग क्या है? पिटिंग बेसिकली इज अ सरफेस फैटिग फेलियर, जिसके कारण जो पिट्स को क्या बोलते हैं? गड्ढा, राइट? पिट जनरल टर्म इज गड्ढा. दैट मींस सरफेस के ऊपर माइक्रो लेवल पे those pits gets created, or you can say that means because of this repeated loading, cyclic loading, and surface के ऊपर क्या होगा? material जो peel off होकर निकल सकता है in the form of small chips, right? Small layers, very small layers come out from the surface. So on the surface you could have many holes, small holes called as pits, that may also produce. So if I say that why we are hardening that surface of that particular gear, why they are hardened, that's what he is in. Gear teeth are made harder to avoid. Why they are made to harder? So basically we want to avoid the surface fatigue failure also. But in general when we talk about, we will say wear is going with a broader term. So it is not that pitting is also correct, pitting can also be correct, but more appropriate out of all these, because wear is a general term. Wear will cover all the things, not only the surface fatigue failure but other kind of wear also. So if material is having a is harder on the surface, then it can avoid other type of kind of surface wear failures also. So I had to choose the best one out of all these, so we will go for the wear. Pitting हो सकता है, it could be. The last question that we see, we were talking in the context of pitting only, surface fatigue failure, surface endurance strength. What was that? That was also, for that purpose we were also hardening it also. But at the same time, wear is not only the pitting, repetitive loading ही नहीं, और kind of abrasion भी हो सकता है उसमें, ये भी आपको आ सकता है, because when they are coming in contact, and अगर थोड़ी सी sliding हुई, तो sliding के कारण क्या हो सकता है, surface के ऊपर, because in gears it is not a perfect rolling, right? Perfect rolling is only at the pitch point. As you move away from the pitch point, you are going to have the sliding also. If sliding is there, then obviously you could have the abrasion also, right? So wear will combine all the things, and therefore not only the surface fatigue failure, abrasion or other things also, so wear will be the most appropriate answer. So these are some of the questions from these areas. Not only these questions, I also told you, and over here also, I think you know, wear strength. There is a equation for wear strength, dPBKQ, right? So this is the wear strength of the gear tooth, right? So what is it? Again, this is the how much tangential, this is the load, tangential tooth load that the gear tooth can carry without any surface fatigue failure. कि ऐसा क्या लोड है जो tangential tooth load में अप्लाई करूं? What is this tangential tooth load that I apply on the gear tooth so that the surface fatigue failure does not take place? It is not, wear is the word used, but it is not a kind of wear we are talking, let's say abrasion we are not talking about. This is specifically, this equation is specifically talking about the surface fatigue failure of the gear tooth because of those repetitive cyclic loading, right? So how we can say, when we say that what is wear strength, we will say it is a tangential tooth load that the gear tooth can carry without any surface fatigue failure, but not any kind of other wear we are talking about. Okay, how we can calculate? We can calculate because of this like this is the diameter of the pinion, this is the width of the tooth, then is K is the load stress factor and K is the ratio factor. So you should also know this formula for this, you should also know the formula for this ratio factor also, because directly he can even give those values also and may cross check your understanding whether you have gone through this or not, right? So that way the questions could also be framed from here also. Okay, so that is all in this particular section for today. So we will come out with a few more topics in the coming sessions. Till then, bye. Thank you.